So hello everyone, my name is Samprat Deshmukh of Branch Computer Science and Engineering, Section A5. I'm here to present you the PPT PowerPoint presentation on understanding quantum gates, which comes under the subject Introduction to Quantum Computing. So let's start. First, we would know that what is like understanding quantum gates in IBM Quantum Lab. So we would see like somewhat synopsis of our PPT presentation, which we would see. This presentation explores quantum gates using IBM Quantum Lab. We will cover CNOT, Toffoli, Hadamard, Fredkin, and Pauli-Gates. Each gate's description through table, matrix, and circuit will be explained. So first question arises in our head, like what is quantum computing? Quantum computing is a type of computing that utilizes the principles of quantum mechanics to process information, offering the potential to solve complex problems faster than classical computers. Unlike classical bits, which are either 0 or 1, qubits can be in a superposition of both states at the same time, allowing for more parallel processing and potentially faster calculations for certain problems. The idea of reversible gate is introduced for the reason of thermodynamics of computation. So this is a statement which actually denotes what is the importance of quantum gates in quantum computing. So let's move to our next slide, which is IBM Quantum Lab. IBM Quantum Lab is like a software platform generated by IBM company. IBM Quantum is a comprehensive platform and ecosystem for quantum computing, offering cloud-based platform to IBM's real quantum computers and simulators, as well as tools and resources for development and education. It allows users to run experiments, explore use cases, and learn about quantum computing through various online resources. Okay, so let's now start with introduction to quantum gates. Quantum gates are like the most prominent thing in quantum computing. So first we would learn about it. Quantum gates are the basic building blocks of quantum circuits. They operate on qubits to perform quantum computations. Quantum gates are reversible operations preserving information. They're represented by unitary matrices. So there are some aspects which are the most important in understanding quantum gates. So first we would see entanglement. As entanglement is suggests multiple qubit gates like CNOT gate entangle states which are crucial for quantum speedup. They speed up the quantum circuits. The second one is the reversibility. Reversibility often suggests that all quantum gates are reversible due to their unitary nature. And the third one is unitary matrices. All the quantum gates are unitary matrices. So these are some of the aspects which we would require further to understand more deeply about the quantum gates. Let's move to our next slide. Okay, so we are now here with our first gate that is CNOT, controlled NOT gate. As the name suggests, it has a control gate and a NOT gate. The CNOT gate is a 2-qubit gate. It flips the target qubit if the control qubit is ket 1. Its operation can be described using a truth table and a 4x4 matrix. So you can see here, it is a 2-qubit gate. Like it flips target qubit if control is ket 1, and we can see over here that we have like input output. You can see ket 0, ket 0. The both when the inputs are 0, we can find it as 0. The same goes with 0 and 1. But if we have the third case, that is ket 1 and ket 0, we can see that both the outputs are ket 1. And if the case in the outputs are both ket 1, then we can see the one output is ket 1 and the second is ket 0. So that denotes CNOT gate. So we can see over the top right side that we have a circuit diagram which denotes the XOR gate over right there, and we can see the output Y and CNOT gate X symbol. So moving to the next slide, we can see the IBM Quantum Lab demonstration. So this is the circuit formed using IBM Quantum Lab of CNOT gate, where we can see the two X gates over right there. Then we can see a CNOT gate. The plus symbol in the blue one is the CNOT gate, and then we can see the two gates which are the measuring gates which measures the quantum gates. So we can see in the last that we can find like a graph like result which demonstrates the final results of the overall circuits. So let's move on to the second gate, that is Toffoli gate. Toffoli gate is the control NOT CC0 gate, as the Toffoli gate is a 3-qubit gate. Now, what the 3-qubit gate is divided into, which is like two gates, which are the control gate, and one is NOT gate, that comprises of the 3-qubit gate. It flips the target qubit if both control qubits are gate 1, and for its function is defined by suitable and an 8 into 8 matrix. As it is a 3-qubit gate, it has an 8 into 8 matrix. So if we see over right here, we can see our circuit over here, that we have gate A1 and the output is gate B1, gate A2 output gate B2, and we have A3, which is the overall symbol of CC0 gate, which actually covers 2 qubit lines, because we have 2 control gates here. So around we can see on the right side that we have a matrix. Matrix is like whole 8 into 8 unitary matrix we can see of CC0 gate. Then okay, so we now move on to the IBM quantum software circuit of CC0 gate. Here we can see 3, because it's a 3-qubit gate. We can see Q0, Q1 and Q2, which have 3, and the second one, which is the blue with 2 dots over there, is the CC0 gate. This gate is represented in the IBM quantum lab, and we can see the 3 measuring gates over right there, which is in the gray color, that denotes the measuring of the quantum software circuit. So let's see our next one. Okay, so next and the third one is the Hadamard gate. I think it's one of the best gates to identify superposition, as it is a single qubit gate. It creates superposition, placing the qubit in a probabilistic state. The truth table and matrix representation define its behavior. The main point of Hadamard gates that it creates superposition, and we can see that the single qubit connected to an edge gate. Its symbol is edge gate, like symbol H written in a square. That's a symbol edge gate, and its matrix can be seen here on the left side, that is 1 upon root 2 in like gate 0 plus gate 1, and on of the gate 1 we can see 1 upon root 2 gate 0 minus gate 1. So we have one positive sign and one negative sign. Then on the right side we can see we have a quantum lab software generated circuit, which we can see in the red color. We have H, that is Hadamard gate, in the Q0 line. Then we can see a gray color symbol, which is used to measuring the Hadamard gate circuit. Okay, so let's move to our next slide. Okay, so now it's time for Fredkin gate, that is a control swap. As the name suggests, we are swapping here qubits, as it is control swap gate. Fredkin gate is a 3-qubit gate, as same as CC0, but it swaps the target qubits of the control qubit is gate 1. The gate is also known as control swap gate, and we can see over right here that Fredkin gate we have a matrix over here, that we have denoted our 3 outputs, that total is 8, as we can see every possible case over right there, which forms also unitary matrix. We can see on the right side that we have Fredkin gate, which has AB plus AC, AB plus AC, and we can, on the B part, we can see our overall circuit diagram, which understands how the Fredkin gate works. So there's more of a possible case that Fredkin gate must offer 3 input and 3 output, and hereafter comes the Pauli gates. So Pauli gates are single qubit gates, as we have seen in Hadamard gates also, but it is divided into X, Y and Z. They perform rotations around the X, Y, Z axis of the block sphere. So the Pauli-X and Y, it both comprises of the NOT gate, as Pauli-X gate suggests that it flips the target qubit, but in the Pauli-Y, it flips the target qubit same as Pauli-X, but it also replaces the behavior of it, the phase behavior of it. And in the Pauli-Z is like more probabilistic, actually it shows more probabilistic behavior about it. So we have 1 0 0 -1 as its matrix, and we can see in the next slide that we have given matrix representation of Pauli-X gate, which is 0, 1, 1, 0. Of Pauli-Y gate, we have 0, minus I, 0. This suggests that we have changed the phase relative state of it. And in the Z, we have 1, 0, 0, minus 1. Okay, so last but not the least, I would explain you the IBM Quantum Lab demonstration, which is helps us to grasp how quantum algorithms manipulate qubits to perform tasks like factorization, search, and secure communication. These gates perform the foundation of quantum algorithms and quantum error correction. So we have a sample circuit over here. The gate labeled H refers to a Hadamard operation, while the second gate is control not operation. The solid circle represents the control qubit, and the circle resembling the symbol plus denotes the target qubit. The dotted rectangle in the figure above therefore represents this operation. So we have like described the overall circuit over here. We have like an example X and Y. The second operation is the control not operation, where Y is the control and X is the target. So we have done two phases of it. First with the H and the second with the control not operation. So we can see over here that we are the I into H, we having a tensor product of I into H, which we can find 1 upon root 2, 1 upon root 2, 1 upon root 2, then minus 1 upon root 2. So this happens in a state where we can find out this matrix. So the final output. So let's create the circuit and Qiskit and check that the calculations are correct. So if you are running the circuit in like Qiskit like formula code basis, so we would write X equals to quantum register 1 comma X and Y equals to quantum register 1 comma Y. The circuit equals to quantum circuit Y comma X. Then we can write circuit.hy, circuit.cx, yx. Then we would display the our gates and the overall circuit. So we would use output equals to MPL, and in the display operator from circuit we can draw latex over it, that it would create the overall circuit. Now when we can see the output matrix, we can see note that the iterative matrix is on the left of the tensor product and H is on the right, which is consistent with Qiskit's ordering convention. So we would remember this thing in finding the circuit's output, as it's mandatory for achieving a good result. So we can see over on the right side of the extreme right, this is the final matrix of our quantum circuit. So now last but not the least, we have our conclusion. Conclusion mainly covers what its application, which are like quantum algorithms, cryptography and simulation. IBM Quantum Lab offers valuable tools for exploration and experimentation. And I would like to thank you all of those who helped me, and our sir PD Bilsari sir. Thank you for achieving me this goal of creating a PPT presentation. Thank you.